projects. In this video, we are going to explain about the project title Optimization of Intrusion Detection using Likely Point PSO and Enhanced LSTM RNN Hybrid Technique in Communication Networks. Introduction. An intrusion detection system is a crucial tool in cybersecurity used to identify potentially malicious activities or abnormal behavior within a network or system. Its primary purpose is to monitor and detect threats that compromise the security of the network. Intrusion detection system uses various techniques to identify threats. These include anomaly detection. This method establishes a baseline of normal behavior and flags any deviation from it has potential threats. Misuse or signature-based detection. This technique looks for predefined patterns or signatures of known attacks within the network traffic. When a match is found, it indicates a potential intrusion. Deep learning methods. These newer techniques utilize complex neural network architectures to analyze large amounts of data and identify patterns that indicate intrusions. Deep learning has shown promise in outperforming traditional methods due to its ability to automatically learn features from raw data. Long short term memory LSTM is a type of recurrent neural network RNN architecture designed to tackle the vanishing gradient problem in training traditional RNNs. In the context of intrusion detection system, LSTM's ability to retain and utilize information over long sequences makes it effective in analyzing network traffic patterns, leading to improved accuracy in intrusion detection compared to conventional RNNs. Traditional techniques like support vector machine SVM, artificial neural network ANN, and random forest have been employed for intrusion detection. While these methods have been useful, deep learning techniques like LSTM and other advanced neural network architectures have demonstrated superior performance in recent studies due to the ability to automatically extract relevant features and patterns from the data. The project aims to further improve intrusion detection system security by proposing an enhanced long short term memory (ELSTM) technique, likely combining LSTM with additional enhancements or optimizations to make it even more effective in detecting intrusions. The use of likely point particle swarm optimization for gradient clipping and feature selection indicates an effort to optimize the ELSTM model by fine tuning its parameters and selecting the most relevant features, potentially improving its performance in detecting intrusions while reducing computational overhead. Objective. The primary aim of the project is to enhance the security measures within intrusion detection system by introducing an improved technique called Enhanced Long Short Term Memory (ELSTM) utilizing recurrent neural network RNN. Additionally, likely point particle swarm optimization (LPPSO) is employed for gradient clipping and feature selection. This combined approach is designed to fortify the capabilities of IDS in identifying and mitigating potential security threats. Current IDS systems often struggle to efficiently detect or combat new or distinct types of attacks. The proposed ELSTM RNN system aims to mitigate these shortcomings by leveraging its architecture's ability to learn intricate patterns and dependencies in data, thus enhancing the overall security of IDS by being more adaptive and capable of recognizing novel threats. The project places emphasis on selecting the most effective and relevant features for intrusion detection. Particle swarm optimization (PSO), an enhanced variant, is used for this purpose. Furthermore, the proposed method's efficacy is evaluated and validated using multiple datasets commonly used for testing IDS systems such as NSL KDD, CIC IDS 2017, CSC CIC IDS 2018, UNSW NB15, and BOT dataset. This comprehensive evaluation ensures the proposed technique's robustness across various scenarios and datasets. The performance of the LSTM RNN framework is assessed using established metrics in machine learning, such as accuracy, precision, recall, and error rate. Additionally, the system's effectiveness is compared against other existing methods like LP boost and deep neural network DNN. Demonstrating its superiority over these methods serves to validate the efficacy and potential advancements offered by the proposed ELSTM RNN approach in enhancing IDS security. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing the necessary Python libraries and packages required for data manipulation, analysis, visualization, and machine learning. Common packages include pandas for data manipulation, NumPy for numerical operations, Matplotlib and Seaborn for data visualization, and specific machine learning libraries like TensorFlow or scikit-learn. Exploring the dataset. The project involves using multiple datasets related to network intrusion detection. Each dataset listed CIC IDS 2017, UNSW NV15, bot IoT data, CSC CIC IDS 2018, and NSL KDD represents different network traffic data containing information about normal and malicious network behavior. Data processing. Removing duplicate data. Duplicate data can skew analysis and modeling results. Removing duplicates ensures that each data point is unique and prevents bias in the analysis. Drop cleaning. This refers to cleaning or handling missing values, outliers, or irrelevant columns in the dataset. It involves dropping columns or rows that are not necessary or hinder the analysis. Data visualization using Seaborn and Matplotlib. Visualization is essential for understanding patterns, trends, and distributions within the data. Matplotlib and Seaborn are popular Python libraries used for creating visualizations such as histograms, scatter plots, bar plots, etc. to gain insights into the data. Label encoding. In the context of intrusion detection, label encoding involves converting categorical variables into numerical format. This transformation allows machine learning algorithms to work effectively on the data. Encoding string to integer. This specifically involves converting string data to integer format using techniques like label encoding, where each unique category gets assigned a unique integer value. Feature selection. Selecting the X and Y data. X typically represents the input features, independent variables used for prediction, and Y represents the target variable, dependent variable. In the context of intrusion detection, X includes various network traffic attributes, while Y indicates whether an intrusion attack has occurred or not. Using mutual info classification. Mutual information is a measure used to determine the relationship between variables. Mutual info classification helps in selecting the most relevant features by estimating the mutual information between each feature and the target variable. Appending selected features to X in target column to Y. After feature selection, the chosen features are appended to the X data, ensuring that only the most informative features are used for model building. The target column Y contains the labels or outcomes indicating whether an intrusion has occurred. Splitting the data to train and test. This step involves dividing the dataset into two subsets, a training set and a testing set. The training set is used to train the machine learning model, while the test set is kept separate to evaluate the model's performance. Building the model. This phase involves defining the architecture or framework of the machine learning model. In this project, it involves creating an enhanced LSTM RNN and integrating it with optimization techniques like PSO to enhance its performance in detecting network intrusions. Training the model. The model is trained using the training data set. During training, the model learns patterns and relationships within the data, optimizing its parameters to make accurate predictions. Flask framework with SQLite for sign up and sign in. Flask is a web framework used to build web applications in Python. In this project, Flask is employed for creating a web interface that allows users to sign up and sign in. SQLite, a relational database management system, is used to store user credentials securely. User gives input. Once logged in, users can provide input related to the network traffic or parameters relevant to intrusion detection. The given input is pre-processed for prediction. The input provided by the user undergoes pre-processing steps similar to those applied to the original dataset before being fed into the model for prediction. This ensures that the input data is in format compatible with the model's requirements. Final outcome is displayed. After prediction, the final outcome, which could be a prediction of whether the input data indicates an intrusion or not, is displayed to the user via the web interface. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is DNN, Deep Neural Network. DNNs consists of multiple layers of interconnected nodes or neurons, each layer performing transformations on the input data to learn representations. They utilize back propagation and gradient descent to update weights, learning intricate patterns and relationships in the data. For intrusion detection, DNNs can discern complex patterns in network traffic, potentially identifying subtle anomalies indicative of intrusions. DBN, Deep Belief Network. DBNs are built from stacked layers of RBMs trained in an unsupervised manner layer by layer, followed by fine tuning with supervised learning. RBMs learn to reconstruct input data and capture high level abstractions. In intrusion detection, DBNs can identify non linear and hierarchical patterns in network traffic, aiding in the detection of sophisticated attacks. ELSTM RNN, Enhanced LSTM RNN. ELSTM RNN is an extension of LSTM RNN architecture designed to capture long term dependencies in sequential data. LSTMs use gates to regulate the flow of information, enabling the model to remember and utilize relevant information over extended sequences. In intrusion detection, ELSTM RNN identifies patterns in network traffic sequences, detecting anomalies or potential attacks based on temporal behavior. CNN, Convolutional Neural Network. CNNs consist of convolutional layers that apply filters to local parts of the input data, capturing spatial patterns. Through convolution and pooling operations, they extract hierarchical representations. In intrusion detection, CNNs recognize spatial patterns in network packets or images representing traffic data, identifying potential threats based on specific packet configurations or signatures. Logistic regression. Logistic regression models the probability of a binary outcome using a linear function. It uses the logistic sigmoid function to map predictions between 0 and 1, making it suitable for binary classification tasks. In intrusion detection, logistic regression classifies network traffic as normal or malicious based on selected features, providing a simple yet interpretable model. Navy base. Navy base assumes independence among features given the class and calculates the probability of a class given the input features using Bayes' theorem. It's efficient, especially with high dimensional data, as it assumes conditional independence. In intrusion detection, Navy base can quickly assess the likelihood of a network event being an intrusion based on feature probabilities. KNN, K nearest neighbor. KNN classifies instances based on the majority class among their nearest neighbor in the feature space. It doesn't explicitly learn a model but uses instance based learning. In intrusion detection, KNN identifies similarities between incoming network traffic and historically labeled instances, classifying based on the majority label among the nearest neighbor. Decision tree. Decision trees create a tree like structure to make decisions by partitioning data based on feature values. Each internal node represents a feature, each branch a decision based on that feature, and each leaf node a class label. In intrusion detection, decision trees uncover rules or sequences of conditions in network traffic data that signify attacks. ADA boost. ADA boost combines multiple weak classifiers into a strong ensemble by iteratively adjusting weights to focus on incorrectly classified instances. It gives more weight to misclassified examples in each iteration. In intrusion detection, ADA boost can improve accuracy by giving higher weight to difficult to classify network traffic instances. Random forest. Random forest constructs multiple decision trees and aggregates their predictions. Each tree is built on a random subset of the data and features, reducing overfitting and improving robustness. In intrusion detection, random forest ensemble nature helps in capturing diverse patterns in network traffic, enhancing accuracy and generalization. Support vector machine with RBF kernel. SVM with the RBF kernel transforms data into a higher dimensional space, finding an optimal hyperplane that separates different classes. The RBF kernel captures nonlinear relationships, making SVMs effective for complex classification tasks. In intrusion detection, SVMs identify boundaries between normal and malicious network traffic based on feature mappings. CNN plus LSTM, convolutional neural network plus long short term memory. This hybrid model combines CNN's spatial feature extraction capabilities with LSTM's ability to model temporal sequences. CNN extracts spatial patterns in network packets, while LSTM learns long term dependencies in sequences. In intrusion detection, this hybrid model captures both spatial and temporal patterns, enhancing detection accuracy. Stacking classifier RF plus MLP plus light GBM. Stacking combines predictions from diverse classifiers like random forest RF, multi layer perceptron MLP, and light GBM using a meta classifier to make final predictions. By leveraging the strengths of different models, stacking aims to enhance the overall intrusion detection performance. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graph. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the comparison graph of bot IoT dataset. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. We will consider the algorithm which is performing best in all the metrics. Comparison graph of CIC IDS 2017 dataset. These are the comparison graph of CSC CIC IDS 2018 dataset. And these are the comparison graph of NSL KDD dataset. And these are the comparison graphs of UNSW NB15 dataset. We have compared the models with the performance metric, accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook folder. This is a Jupyter notebook folder which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Now use the cd command followed by a space and then paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. Here we need to enter all these details to register. But I have already registered. So click on sign in link here. So here we need to enter the username and the password and then click on login. We have logged in successfully. So here we can see the prediction link. We can execute the project using the different data sets. First, we will execute the project using the NSL KDD dataset. So click on it. So here we need to enter these parameters to predict whether intrusion is detected or not. Before entering the parameters, let us understand the parameters. So the first one is service. Type of network service for the connection, example HTTP, FTP. Flag, connection status indicator, example FIN, SYN, RST. SRC bytes, that is source bytes. Bytes sent from the source in a connection. DST bytes, that is destination bytes. Bytes sent to the destination in a connection. Count, number of connections to the same destination host. Error rate, percentage of connections with the SYN errors. Same SRV rate, percentage of connections to the same service, different SRV rate, percentage of connections to different services, DST host SRV count, number of services on the destination host, DST host same SRV rate, percentage of connections to the same service on the destination host, DST host different SRV rate, percentage of connections to different services on the destination host, DST host error rate, percentage of connections with SYN errors on the destination host. Now we will enter the parameters value. So I'm entering the value. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS, that is distributed denial of service. Now we will enter another set of parameters and check whether attack is detected or not. So here I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is probe. Now we will enter another set of parameters. So click on prediction link and now click on NSL KDD dataset. So here I'm entering the values of another set. So here I have entered another set of parameters. Now click on predict button. So here we can see the result. There is an attack detected. Attack type is R2L. In this way, just by entering the parameters, we can predict whether attack is detected or not. Now we will do the execution using another dataset. So click on prediction link and select the UNSW NB15 dataset. Now we need to enter these parameters value. Before entering the parameters, let us understand the parameters. Duration of the connection or the length of time for which the connection lasts. S bytes, that is source bytes, number of bytes sent from the source in the connection. D bytes, that is the destination bytes, number of bytes sent to the destination in the connection. Rate, average transfer rate for the connection, possibly measured in bits per second. STTL, that is source time to live, TTL, indicating the maximum number of hops or routes the packet can pass through before being discarded. DTTL, that is destination time to live, TTL, similar to STTL but for the destination. S load, average outgoing traffic from the source in bytes per second. Deload, that is destination load, average incoming traffic at the destination in bytes per second. DINPKT, that is number of packets destined for the destination. S mean size of packets sent from the source. D mean, that is destination mean size of packets sent to the destination. CT state, TTL, the number of concurrent connections to the same state, that is the same set of attributes, and TTL value. Now let us enter the value for these parameters. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS, that is distributed denial of service. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters now. So here I have entered another set of parameters. Now click on predict button. So here we can see the result. There is no attack detected. It is normal. In this way, just by entering the parameters, we can predict whether attack is detected or not. Now we will do the execution using another dataset called CIC IDS 2017. So click on it. So here we need to enter all these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is forward packet length standard deviation. Standard deviation of the forward packet length. Forward packet length mean of the forward packet length. Forward packet length maximum. maximum length of the forward packet, forward segment size average, average size of the segments in the forward direction, packet length standard deviation of the packet length, flow IAT standard deviation of the flow inter arrival time, backward packet length standard deviation of the backward packet length, backward segment size average, standard deviation of the backward length, packet size average, average size of the packet, subflow forward bytes, bytes of the forward subflow. Now let us enter the parameters. So I'm entering the parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is no attack detected. It is benign. Now let us enter another set of parameters and check whether attack is detected or not. So click on prediction link here and then click on CIC IDS 2017 dataset. So here I'm entering another set of parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is FTP brute force. In this way, just by entering the parameters, we can predict whether attack is detected or not. Now click on prediction link. Now we will execute the project using another dataset called CIC IDS 2018. So click on it. So here we need to enter all these parameters value to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is forward packet length standard deviation. Measures variability in forward packet sizes. Forward packet length mean represents average size of forward packets. Forward packet length maximum denotes maximum size of forward packets. Forward segment size average indicates average size of forward segments. Packet length standard deviation measures variability in packet lengths irrespective of direction. Packet length standard deviation measures variability in packet lengths irrespective of direction. Flow IAT standard deviation represents variability in inter-arrival times of flow. Backward packet length standard deviation measures variability in backward packet sizes. Backward segment size average indicates average size of backward segments. Packet size average denotes the average size of packets regardless of direction. Subflow forward bytes represents the bytes in the forward subflow segment. Now let us enter the parameters. So I'm entering the parameters value. So here I have entered all the parameters. Now click on predict button. So here we can see the result. There is no attack detected. It is benign. In this way, by entering the parameters, we can predict whether attack is detected or not. Now let us execute the project using another dataset called bot IoT. So click on it. So here we need to enter all these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is protocol. Specifies the communication protocol used, packets, total number of packets in the connection, bytes, total number of bytes transmitted, source packets, number of packets sent from the source, D packets, that is destination packets, number of packets sent to the destination, S bytes, that is source bytes, number of bytes sent from the source. Let us enter the parameters. So I'm entering the parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is no attack detected. It is normal. Let us enter another set of parameters and check whether attack is detected or not. So I'm entering another set of parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see the result. There is an attack detected. Attack type is DDoS, that is distributed denial of service. In this way, just by entering the parameters, we can predict whether attack is detected or not. Now click on sign out button here. Conclusion of the project. The proposed combination of the enhanced LSTM, eLSTM within the recurrent neural network RNN framework, augmented by likely point particle swarm optimization, LPPSO for gradient clipping and feature selection, has demonstrated promising outcome in fortifying security within intrusion detection system IDS. This suggests that the integration of these techniques contribute to enhancing the effectiveness of IDS in identifying and mitigating security threats. The performance of the proposed method was rigorously evaluated using diverse datasets such as NSL KDD, CIC IDS 2017, CSC CIC IDS 2018, UNSW NB15, and BOT dataset. Utilizing these varied datasets for validation and testing indicates a comprehensive analysis suggesting that the proposed framework's efficacy was tested across different scenarios and types of attacks commonly found in communication networks. The results indicate that the proposed system exhibited significantly reduced training times compared to other models across various classes. This suggests that the eLSTM RNN framework coupled with LPPSO not only enhances security but also operates efficiently in terms of computational resources and time required for training, an essential factor in practical deployment. The eLSTM RNN framework surpassed the performance of LP Boost and DNN deep neural network methods across multiple metrics like accuracy, precision, recall, and error rate. This demonstrates the superiority of the proposed approach in effectively identifying and addressing security threats within communication networks. The observed outcomes validate the effectiveness of the eLSTM RNN framework in augmenting both security and performance within IDS. This suggests that the proposed methodology is a promising approach for enhancing the capabilities of intrusion detection system, potentially leading to more robust and efficient security measures in communication networks.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.